the boundary condition. Let's take a look at it. Uh, these two boundary conditions I'm going to leave to you. Just insert f as we found here. For instance, take the third derivative of f and put x is equal to 0 and equate the whole thing to 2 and figure out the constants. But there's one of them which is pretty interesting in here. I'm going to do this. So I'm just write it out here for clarity, for sake of clarity. So the thing was as follows. I'll write it here. So I said that the function should go to 0 at x as x goes to infinity. So we wrote it out in this manner. We said the limit of f at a, at some point a, as a goes to infinity equals 0. Okay. Now let's take a good hard look at the family of solution that we found in here. There are essentially two terms. There is this guy on top, e to the power plus beta x times something, so there's one term on top. And there's another term, it's summed with another term on the bottom. Okay. So now let's take a look at it. What will happen if x grows and grows and grows? Okay. So we had two functions. Okay, let me write everything. Yeah. Okay, it's clear. All right. So let's say this is x and this is something. Okay. I'm going to draw these two functions. See, e to the power beta x is multiplied by something, but by the way, let me say something. Let's take a look at it. Inside the parentheses here, we have cosine and sine. Okay, the sine and cosine, the cosine and sine could be at most +1 and at least -1 multiplied by d1 and d2. Okay, so they're kind of finite, and the values are finite. They couldn't be infinity or anything. This is like a finite number multiplied by e to the power beta x. Okay, so let's see what will happen as x grows in here. Let me draw e to the power 0 is 1, and this thing comes from minus infinity and goes all the way up. So this fellow is e to the power x. Okay, you can multiply by whatever you want here, a finite number. You can multiply the exponent by anything, by any positive numbers, but essentially the trend is like this. It starts from minus infinity and goes all the way to plus infinity. All right. What about e to the power minus beta x, this guy? This guy goes from some real huge number and goes all the way down to 0. Okay, and this guy is e to the minus x. Okay, so we saw the trend. So it's like as x grows larger and larger, this e to the power minus x tends to 0, but e to the power plus x tends to infinity. Okay, now let's go back, let's retreat back to our function here. So it's like as x grows, this term would grow with it. And if x goes to infinity, it's very, very large. This term would be very, very, very large. Okay. What about this term on the bottom? As x grows larger and larger, this term will become smaller and smaller. And at infinity, e to the power minus beta x, as we showed here, would essentially be 0. So this term would cancel out entirely at 0. But this term would be infinity, would become very, very large. But let's take a look at it. Our boundary condition told us that we want the function as at infinity, at x grows very large, to be 0. So this guy does what we want, but this guy doesn't do that. So we kind of need to cancel out this first term on top. But how could we do that? E to the power beta x, beta could not we couldn't do anything with beta, and x is growing to a very large number, infinity. So we cannot do much about this term here. But what about this term in the middle? We could do something about it. We could say this term in the middle is entirely zero. I could do that. I could say d1 cosine beta x plus d2 sine beta x is equal, beta x is equal 0. Okay. So that's pretty interesting. Let's see what this guy is telling us. This guy is telling us that something multiplied by a cosine plus other thing multiplied by a sine is equal to 0. Now let's take a look at it. There is no way that I can, or maybe there is some ways, some very special ways that I can add a cosine by a sine and I have a 0. But for all x's, I could not have something like that. Let's take a look at it. Let me draw sine and cosine. Let me see on a plot, and I think it's more illustrative. So this is a sine. Okay, and this guy is a cosine. Okay, so this is a cosine and this is a sine. Maybe I could find some combinations of these two that will make it 0, but I cannot do it everywhere. For instance, I could probably at pi over 2, I could do something. I could say for instance, this guy at pi over 4. Sorry, this guy and this guy would cancel each other out, and I could add them up together with some combinations, or I could do something else somewhere else. But I cannot do it everywhere. It just, for all x's, that thing could not happen. I cannot satisfy this guy. But there is only one way that I could absolutely make sure that this guy is equal to 0. The only way is that d1 is 0 and d2 is 0. That's the only way. And it's also pretty nice, because let's take a look at it. If these two guys are 0, then let's take a look at our family of solution here. There it is. If we make d1 0 and d2 0, we essentially get rid of this inconvenient term with e to the power plus beta x. So we make sure that our solution would not blow up as we go to x equal infinity. So that's pretty neat. Let me take that and just get rid of d1 and d2 in here and write out the family of solution. So I'll write out everything. So the family of solution will become, without d1 and d2, equal to e to the power minus beta x. That's a good term, which made our solution go to 0 at x equal infinity. X goes to infinity. E to the power minus beta x times cosine, d3 cosine beta x plus d4 sine beta x. Okay, that was pretty neat. Now we ended up with only 2 unknown constants, and you guys have the differential equation, and you have the boundary conditions. You have 2 equations here. You could insert f, this guy that we just found here, into these 2 equations. For instance, take the third derivative, set x equals 0, and equate the whole thing to 2. And the same thing for the other one. And find d3 and d4. Find the solution as an exercise. I got lost of which exercise it is, but as an exercise, find the solution and plot f against x. And you will see that as x goes to infinity, f becomes 0. So that would be all. Let's move on to the next differential equation.